Good morning, everyone, and welcome to our day 2 of our HDF user group event. And without any delay, I will invite our first speaker, Houjun Tang, with Async Cloud, transparent asynchronous I/O using background threads. So Tang, please, floor is yours.
All right, thank you, Elena. Good morning, everyone. I'm Houjun Tang from Berkeley Lab. I'm the main developer for the Async Cloud, and over the past couple of years, a lot of people are also contributing to this work. And today I will be talking about it and show some use cases and results. So first of all, why do we want to develop this Async Cloud? So for many applications, especially scientific simulations, they output write data or checkpoint data periodically, and as applications are moving into GPU or other accelerated computing, the CPU that is doing all this I/O, while they are doing it, the computing units like the GPU are sitting idle, so it's kind of a waste of resources to wait for all the I/O activities to finish. And enabling asynchronous I/O for these applications could potentially save a lot of time, as shown in this figure. So when the application has a compute phase and a I/O phase, for example, writing data periodically, if we can enable asynchronous I/O or asynchronous write and overlap the write with the compute, then the application can save a lot of time. As the name suggests, Async Cloud is a HDF5 wall connector, and I will give a brief introduction of what is wall. So wall or virtual object layer is a layer in the HDF5 library. It's similar to the PMPI in the MPI library, where a user can intercept the HDF5 calls and then do some either capture some information, or as for async wall, it will queue a number of I/O tasks and put it into a background for execution. So in virtual object layer, there are two types of walls. One is called pass-through, one is terminal. For pass-through, they are, as the name suggests, it is just passing things through, and they are not really interacting with the file system. And as a result, pass-through can be stacked on top of each other. So for example, there are asynchronous walls and there are caching walls, and there is a use case to stack the cache wall and async wall. And then after the pass-through wall, the HDF5 library has to reach to a terminal wall. So terminal wall most frequently uses the native HDF5 terminal wall, which interacts with the file system and read and write data. There are also other terminal walls, like Jerome introduced the Deos wall yesterday, and there are like REST walls that interact with cloud storage, things like that. So for async wall, here's a brief introduction on how to use it. So in preparation, the async wall requires the latest HDF5 developed branch. And also for the asynchronous execution, we use the Argobos as a thread engine. So those codes must be compiled before compiling async. And to note that for the HDF5, we use develop branch, and we have to enable the thread safety support while compiling it. And then you compile Argobos, and after that, you can compile the async wall connector. And once everything is compiled and no errors is observed, to use it, the user needs to set some environment variables to activate the use of async wall. So for example, they need to set the LD library path, and as well as the HDF5 plugin path, and HDF5 wall connector variable to let the HDF5 library know that it should find and use the async wall. And we have detailed instructions and documents in the Reader Docs repository, which can also be found in the GitHub repository. And we are working on a spec build, so all of this can be replaced with just one spec install HDF5 async wall command. In fact, we have a spec recipe, but it is not in the spec official repository. So if you are too eager to try, you can look for the spec recipe in the async wall GitHub repository and just copy that to a spec installation and do the spec install. So in async wall, there are two modes. One is called implicit and the other is called explicit. So for implicit, it is for unmodified HDF5 applications. So application does not need to change the thing with their code. They just need to specify the environment variables to enable async wall. However, there are a number of limitations with this mode. Most importantly, the dataset read and write, they are always blocking or synchronous due to the fact that if we made it asynchronous, then many application codes will simply block because they previously they think that every HDF5 I/O call is blocking and they may free the buffer, but in fact, when running with async wall, that is not the case. So the HDF5 I/O call may return immediately, and while the operation is in a queue and has not been executed, and freeing the buffer means that the data write will result in a disaster. But for implicit mode, is really just trying things out, and all the metadata operations are asynchronous. So it's if the application has a metadata heavy workload, then it's worth a try to use the implicit. Also, implicit works well with cache vault, which is the next talk by Huihua. So if you want to know more about that, then stay tuned with the next talk. And then for the explicit mode, so explicit mode is really the desired choice for application to move to the asynchronous I/O. So the explicit mode uses the event set API to manage asynchronous operations. So an event set is basically a bundle of operations that the user can operate as a group instead of individually. And the explicit mode can extract more performance. So both the dataset read and write are fully asynchronous, and but still user needs to make sure that the buffer is not freed until the asynchronous execution has completed. So I will talk a little bit more in the next few slides. So for the event set API, this is a new API introduced into HDF5 library. So basically, we have an asynchronous version of all the HDF5 I/O calls. For example, H5F create, we have an async version of F create underscore async. And there's one parameter added to the parameter list. So that's the event set ID. So by switching to the event set ID and the async version of the HDF5 APIs, application can manage and control the asynchronous operations. For example, users need to create the event set first, and then associate that event set with one or more operations. And then if the user wants to wait or just like MPI barrier to guarantee that all the asynchronous operations have completed, then they do this wait, and afterwards they do the ES close, just like all the HDF5 close routines. And then for error checking, so async errors can be tricky. So because they do not happen as you call the asynchronous APIs. So by default, we will not report any of the errors into the SDDER, as is the case with the non-async HDF5. So we capture and record all the error information into the ESID that is associated with the operations, and the users have to check the ESID with the HDF ES get error info or other error checking routines to make sure that no error happens. So here is a brief example of how users should convert their existing code to use the async event set APIs and fully utilize the asynchronous I/O feature. So first of all, since async I/O often involves in MPI operations, we require to use MPI thread multiple to ensure the MPI thread safety and not confuse MPI with different calls from the application thread and the async background thread. So MPI init will need to change the MPI init thread with thread multiple support. And then, as I mentioned previously, we are using the event set APIs. So an event set needs to be created with HDF5 ES create. And then it's basically converting all the existing H5 function calls to their async versions. So file create changes to file create async and with the ESID as the last parameter. And so group create, dataset create, and dataset read or writes. And also a close can also be async. So all of these operations, they are non-blocking, so they will return immediately. And an ideal case is that application has an I/O phase and then has a computation phase. And the goal is to overlap the I/O phase with the computation phase. So previously, with a non-async version, all of these are blocking. So up to here, at file close time, every operation should finish. But with the async, up to the file close, first file open or file create operation may not even happen yet. So in this way, we can overlap all these operations in the asynchronous I/O wall connector background thread, and then overlap them with the computation. And at the end, when the application finishes everything, all is just want to wait here and make sure all the previous operations have finished. They use this ES wait. You can specify to wait for error, or you can specify a timeout value. And then finally, you close the event set. So this is just gives a basic idea of how existing application can convert their code to use these new APIs. And some notes with the error handling. So with asynchronous execution, if any operations fail, all of these dependent children operations will not be executed because they will all error out anyway. For example, if a file create failed, then any group raised in that file or dataset read or writes will not be executed at all, and they will all just fail. So for error message recording, we do append additional error message into the HDF5 error stack, which can be checked with the using the event set APIs on an event set ID. So for example, here we have a dataset create failure, then we just add that to the error stack, and the user can query those and print those out as needed. So there is currently there is one limitation with the HDF5 library is that when the thread safety support is required, is enabled, there is a global mutex, and the global mutex sometimes prevent us from executing the task asynchronously, because both the application, when they call any HDF5 API, they will acquire the global mutex, while for the asynchronous wall background thread, when they execute anything in the background thread, they will also need to acquire that global mutex. And in some cases, if both threads they execute things in an interleaved fashion, then it will effectively make everything asynchronous. So the way we work around this is that we have the async wall to detect the application's status on the HDF5 library calls, and we only start at the execution in the async background thread when we think that the application is not busy issuing HDF5 I/O calls. So basically, we do queue a number of operations, and then we use some counter to detect the application status. And once we found that application is idle or moving into a compute phase, then we start the execution, and that will repeat for the entire runtime of the application. And internally, we do some task dependency management because we are executing things asynchronously. So a lot of things need to be guaranteed for the data consistency, but these are all transparent to the user. So user doesn't need to worry about this. These are all handled internally. So for example, there are some rules like all I/O operations can only be executed after a successful file create or open, and file close can only be executed after all previous operations of the file. And there are some additional requirements on the read or write operations, the order of them to make sure data is consistent, and some special handling with the collective operation. So we are only allowing one collective operation to be executed at a time to make sure no deadlock happens. So over the couple of years working with applications and trying out with small to large scale runs, there are some best practices advices. So basically, to achieve the best performance, the application should have a sufficient non-IO time for the async wall to overlap the async computations. Otherwise, if the compute is too short and the IO happens too frequently, there may not be enough improvements. And we have a new feature developed recently to avoid the application status check. So if the application clearly knows that it has an IO phase that creates a file, writes some attributes and data sets, and then closes it, then it can inform the async wall to avoid sometimes costly application status monitoring by setting an environment variable. In this case, all the asynchronous operations will only start executing at file close time, and no application status monitoring overhead exists in this case. And also for some applications that are just write only and has very simple accesses, we have this automatic user buffer management, because otherwise we require the application to manage the user buffer for writes. Often cases, the application needs to do a double buffering, but if the application does not want to do that, we provide a very simple version to malloc and memcopy the user's buffer at the HDF5 API when it first enters the async wall, and then we will free the buffer after the operation has completed. And in this way, the application does not need to care about doing double buffering by themselves and leaving it to async wall. So there are some additional options to specify how much additional memory that the async wall can use to malloc. And when that limit is reached, then async wall will automatically enters into a synchronous mode and then performs the write before that memory is freed. So there are also more advanced capabilities available when stacking async wall with cache wall. So cache wall can enable a memory cache as well as no local SSID cache. So those are more advanced features, and you can expect more from the next talk.
Tang, I think we are running out of time. So maybe
okay, yeah, so only a few more slides. So here are some results. We have tested with some benchmarks. WPIC is a write-only benchmark, and BDCAS is a read-only benchmark, and they are writing. Here they are reading or writing the same amount of data, and we do see significant speed up when using async wall. And we also work with the AMR-EX framework. So we integrate async APIs into the AMR-EX, and AMR-EX have two applications. One is got NICs, another is casual. So we also observe the significant speed up when the application is writing multiple time steps. So some future work, we are working with small applications for async integration and some further optimizations such as merge compatible operations and also dynamically setting the tuning parameters. And we are also currently studying the effects where using async wall has some interference with the application's own MPI communications. But some early results show the overhead may not be that significant. We only observe like 2 to 5%. So that will be all. Any questions?
Thank you, Tang. Since we don't have much time for the questions, maybe you can take the questions in the chat. There are one question coming in, and then more questions may be coming in. So